October 30th, 2024, the Fukushima Daiichi nuclear power station. Members of the fuel debris retrieval team waited with bated breath as they intently watched the monitors. They were seeing the bottom of a reactor where melted fuel debris had accumulated. This debris melted through the reactor pressure vessel during the nuclear accident that occurred as a result of the Great East Japan earthquake 14 years ago. At the top right of the screen, an end jig, operated remotely, successfully grasps a piece of fuel debris amidst the high radiation. Ide Hiroshi is on the fuel debris retrieval team.
When the device successfully picked up the debris, there was an audible wow from everyone.
The problem was how to retrieve fuel debris when the environmental conditions were unknown and no one could enter. Specialized equipment was developed and numerous preliminary investigations were conducted. Arai Tomoyuki is the leader of the fuel debris retrieval team.
Due to the high radiation levels, it was a challenge to design devices that minimize human involvement as much as possible.
This is Chief Decommissioning Officer Ono Akira.
Being able to retrieve fuel debris from a high radiation environment using remotely operated equipment was an extremely significant achievement. The fuel debris is being subjected to various types of analyses, and I believe that the information we obtain will be incredibly useful in the future.
The fuel debris sample was about 5 millimeters in diameter. While this is only a small fraction of the amount remaining inside the primary containment vessel, its retrieval is an unavoidable obstacle to reducing radiation levels, which is essential for decommissioning. 14 years since the accident, this marks the first step of a new journey. The retrieval of fuel debris here is unknown territory. This program will showcase the efforts of those on site, undertaking this unprecedented challenge. The Fukushima Daiichi nuclear power station faces the Pacific Ocean. Each day, between about 3,500 to 4,700 people work to decommission the plant. With 6 reactors, the power station is an expansive facility that was a major power supplier for the Tokyo metropolitan area. The Fukushima Daiichi nuclear power station accident that occurred in the wake of the Great East Japan earthquake on March 11, 2011, resulted in the release of radioactive substances. Following the accident, workers needed to wear protective clothing and full face masks everywhere on site. Since then, decontamination efforts have progressed to the point where workers need only wear regular uniforms and simple dust masks in 96% of the site. The Tokyo Electric Power Company is moving steadily forward with decommissioning to further reduce radiation risks. One of the most difficult tasks is the retrieval of fuel debris. The biggest challenge for decommissioning is how to ensure safety while working in an environment with extremely high radiation levels. The superintendent of the Fukushima Daiichi nuclear power station is Taminami Tatsuya.
Making sure work is carried out safely on site is always our first consideration. For example, there are tasks that utilize technology such as remotely operated robots and robotic arms or other high-tech equipment. However, people are needed to deploy and operate these devices in the field. And continuously, people will still be working at the decommissioning site for 30 to 40 years.
The retrieval of fuel debris is certainly the most difficult task in the decommissioning of the Fukushima Daiichi nuclear power station. Of the plant's 6 reactors, Units 1, 2, and 3 suffered core damage that resulted in the same issue. The debris is a mixture of fuel and structural components, such as the cladding tube that covered the fuel rods, that melted together and then solidified. In charge of the fuel debris trial retrieval is Arai Tomoyuki. Arai worked in the maintenance division at the plant when the earthquake occurred. Having witnessed the accident and understanding better than anyone the dangers of radiation, he now is in command on the front lines, ensuring the safety of decommissioning every day.
In April 2021, I was assigned to manage the fuel debris retrieval team, where I am still the manager. We knew that the most challenging part of the work would still be to come, and although I wasn't expecting to be assigned to the project, I accepted the challenge and that it would be difficult moving forward.
Due to the high radiation risks, a variety of remotely operated robots were developed to investigate the conditions in the field without having to rely on a human presence. For example, to investigate fuel debris conditions, a submersible robot was used to investigate the bottom part of the primary containment vessel, which is flooded with water. This is footage from 4 small drones investigating the interior of the primary containment vessel. Because the signal used to control the drones is cut off by the primary containment vessel, a snake-like robot was deployed to relay the signal to the drones. This footage will be analyzed to deliberate how to retrieve the fuel debris. At Unit 2, where a fuel debris sample was successfully retrieved, Arai and his retrieval team used an opening leading into the primary containment vessel to deploy remotely operated equipment in January of 2012 and conducted 6 preliminary investigations.
The first 3 investigations were conducted when radiation levels inside the reactor building were much higher than they are now, and the only penetrations that allowed access to the containment vessel were very small. We therefore focused on investigating temperatures and water level to ascertain the environment inside the primary containment vessel.
The retrieval team inserted a device similar to a fishing rod through the opening. A camera attached to the tip of the rod was used to investigate the conditions inside the primary containment vessel.
During the final investigation, we confirmed that small pebble-like debris could be moved. These investigations gradually improved our understanding.
The investigations of Unit 2 showed that the most optimal route for retrieval was to use an opening in the side of the primary containment vessel, called the X6 penetration. The X6 penetration was originally used to access and replace equipment inside the primary containment vessel and has a diameter of approximately 55 centimeters. The team hypothesized that they might be able to successfully retrieve fuel debris if they could insert remotely operated equipment through this opening.
One reason why retrieving fuel debris from Unit 2 seemed comparatively more manageable is because the core of the Unit 2 reactor had melted less, meaning that radiation levels inside the reactor building were lower than the other units. The second reason was that even though there are fewer penetrations leading to the bottom of the reactor pressure vessel, over the course of 6 investigations, the X6 penetration proved to be a viable option for fuel debris retrieval at Unit 2.
The first step was to install an isolation chamber at the entrance of the X6 penetration. This prevented gases from inside the primary containment vessel from leaking out during the retrieval process, ensuring that the surrounding environment would not be affected. The isolation chamber was pressurized using nitrogen to prevent stirring up dust and particles. Next, a dedicated device was inserted into the isolation chamber, and the hatch of the X6 penetration was opened. Preliminary investigations showed that the opening was blocked by various deposits. These needed to be cleared before the remotely operated retrieval equipment could be inserted.
During the preliminary investigations, we lightly prodded the deposits and found that they were firm but had some elasticity. From this, we gathered that they could likely be moved if subjected to enough force. Based on this information, we used 3 different methods to remove the deposits. The first method was to attach a plate to the end of a rod and use it to push the deposits. The second method involved using low-pressure water to push and wash away the deposits. And the third method entailed using high-pressure water to blast the deposits away. These 3 methods were combined to successfully remove the deposits.
Thanks to the preliminary investigations and the deposit removal devices, they cleared the deposits from inside. This enabled them to secure enough clearance to insert the retrieval equipment into the primary containment vessel. In the event that the fuel debris retrieval was successful, the device would re-emerge holding the fuel debris sample. They therefore built an enclosure that would safely cover both the device and the fuel debris sample.
We knew that the retrieved fuel debris sample could not be directly handled by people, so it was crucial to ensure that it didn't contaminate the surrounding workspace while being removed. We needed a way to safely contain it, so we built a special enclosure designed for this purpose.
This is the retrieval device that was used. It can be extended and retracted much like a telescope. At the tip of the device, there is a mechanism resembling a fishing rod that is used to grasp the fuel debris. Training was conducted on a mock-up of the Unit 2 primary containment vessel, right up until just before the actual retrieval attempt. The remotely operated equipment was fed through the penetration, and every step of trial retrieval was thoroughly rehearsed. These rigorous repeated tests ensured that the team was ready.
There were 2 major difficulties during the retrieval process: radiation and human involvement. Since there are many people involved in the retrieval work, preparation was the key to ensure they could perform their tasks without error. Also, due to the high radiation levels, it was a challenge to design devices that minimized human involvement as much as possible.
Arai was faced with the difficult decision of how much of the task could be performed while prioritizing the safety of workers during the limited time of the fuel debris retrieval test, and how much could be done by remotely operated equipment.
The most difficult part was balancing human involvement with the use of remotely operated devices. However, our past experience enabled us to determine what could be handled by field workers, and based on that, we manufactured equipment and conducted training to handle the other challenges.
With all preparations complete, trial fuel debris retrieval began in September 2024. The telescopic device was passed through the X6 penetration, and an attempt was made to retrieve small pebble-like pieces of fuel debris from the bottom of the primary containment vessel. On October 30th, 2024, they were finally able to grasp a 5mm pebble-like piece. This is the actual piece of fuel debris that was retrieved. By November 6th, it was safely inserted into a transportation container, and on November 7th, the container was placed into another dedicated container, marking the successful completion of the trial retrieval. This retrieval attempt represents a historic first step. At this important juncture, it was Ide Hiroshi who gave precise instructions to operations personnel, remotely operating the equipment.
On the day we retrieved the fuel debris, I was in the remote operations room. There were quite a few people affiliated with the program in the room, and I remember when the device successfully picked up the debris, there was an audible wow from everyone. I felt a great sense of relief that we had finally reached this point. I'm from Namie Town, which is less than 10 kilometers from the Fukushima Daiichi nuclear power station, and within an area designated as a difficult-to-return zone. I am determined to contribute to the decommissioning work so that the local residents can return to their homes.
Taminami Tatsuya, the superintendent of the Fukushima Daiichi nuclear power station, was also there that day to witness this significant milestone.
I thought, we finally got a sample. Even though it's only a small piece, the joy of successfully taking this huge step was immense. When working on such a difficult project, we often feel the pressure of not being able to fail. In these moments, I believe it's crucial to maintain motivation so that everyone can continue to perform admirably. I always tell the team, let's keep our heads up with pride and move forward with decommissioning, almost like a team motto.
The retrieved fuel debris was transferred to the Japan Atomic Energy Agency's research facility in Ibaraki Prefecture for analysis. This retrieved fuel debris sample will be a vital specimen for the decommissioning work ahead. At this research facility, the radiation levels and composition of the sample are being analyzed to ascertain its properties and attributes. This information will be used to deliberate large-scale retrieval in the future. The analysis is being led by Maeda Koji. He has been involved in the research and development of nuclear fuel, as well as tests on the integrity and safety of nuclear materials for about 30 years.
The sample obtained from the trial retrieval of fuel debris is initially examined using non-destructive testing methods, such as X-rays and CT scans, the same used to view the interior of the human body, to investigate the internal structure of the debris sample. As for the surface, we first check the distribution of elements using tools like field emission scanning electron microscopes, to see which elements are present on the surface without damaging it. to determine if uranium is present in particular. We also check whether elements from the structural components of the reactor core are present.
Going forward, the sample will be broken down to perform more detailed analyses of fuel debris composition. This will make it possible to deduce the path which the molten debris took and the mechanism by which it was formed.
The information we obtain will be used to determine how to retrieve, or cut away, if you will, the fuel debris on a large scale. Our data will help address each and every challenge of decommissioning, and will hopefully be used effectively to deliberate future steps.
An essential part of the decommissioning process is addressing contaminated water. Rainwater and groundwater enter the reactor buildings of the Fukushima Daiichi nuclear power station and come into contact with fuel debris or water contaminated with radioactive substances. Through multiple countermeasures such as groundwater pumping, the daily volume has been reduced to about 1/7 of its previous level. The contaminated water is treated using multi-nuclide removal equipment known as ALPS, which can remove radioactive substances except for tritium to levels that meet national regulatory standards. The ALPS-treated water is stored in approximately 1,000 tanks within the power plant premises. Tritium is a radioactive substance that emits very weak radiation, which cannot be removed by ALPS. Therefore, it is diluted with a large volume of seawater to ensure that its concentration is less than 1/40th of national regulatory standards and below approximately 1/7 of the World Health Organization's drinking water standard. Since August 2023, a special pipeline built 14 meters below the seabed and stretching a kilometer offshore has been used to discharge this diluted ALPS-treated water into the sea. International Atomic Energy Agency experts have conducted objective reviews to ensure that the discharge is consistent with the relevant international safety standards. Over the mid and long term, these reviews will be conducted before, during, and after the discharge of ALPS-treated water. Further investigations are being carried out to ensure the safety of the discharged water. Seawater is sampled from 36 locations near the discharge points of the power station and tested by the Tokyo Electric Power Company. Fish are also tested from 11 locations and seaweed from 2 others. The analysis results are publicly disclosed to affirm the safety of the water and marine organisms.
Monitoring results until now confirm the discharge remains below national regulatory standards, ensuring its safety. In addition to our own verification, monitoring conducted by Fukushima Prefecture and the government has also confirmed the safety of the discharge. Furthermore, data is reviewed as part of the ILC, an international analysis conducted by the IAEA.
Together, and had to have a high degree of community scientific.
Lake Barrett, who was the on-site director for the U.S. Nuclear Regulatory Commission, played a key role during the 3 Mile Island accident in the United States in 1979. Fuel debris retrieval began 6 years after the accident. 11 years later, 99% of the fuel debris, approximately 130 tons, had been successfully retrieved. Barrett visited the Fukushima Daiichi nuclear power station multiple times, offering guidance on their ongoing efforts based on his extensive expertise in decommissioning.
Maintaining safety in handling all the radioactive materials on that site to protect the public and to protect the workers is paramount and the first order to have that safety culture in place. You need to continue to focus on reducing the risk of the radioactive materials as you move forward toward getting better, more sampling, more data from inside to design new pieces of equipment, new approaches to remove the fuel debris and to be able to handle the waste that you've created so far and will be retrieving in a safe manner. And I think the engineering staff has been very dedicated and worked very, very hard, and all the people at that site do. And one thing I'm always impressed as an American when I would go over there is the individual dedication of all of those people. They feel a responsibility for what happened, and they want to basically make it right. And that dedication, that sense of honor, sense of responsibility is so refreshing for me to see when I'm there. Well, they've made a lot of progress, over the last almost 14 years here. There's a long way to go, but it's going well. They've had a good safety record, and they will continue doing it that way.
As we continue with this work, I am sure that there will be challenges which arise that we can't anticipate. But we can't be afraid of facing such issues, because then no progress will be made. The key is to prepare thoroughly and take on these tasks after making the best preparations possible. We hope to continue to incorporate and apply various knowledge, experience, and technologies from around the world. The decommissioning of the Fukushima Daiichi nuclear power station is going to take an extremely long time. It's crucial for us to ensure the decommissioning process is carried out safely so that society can feel at ease. As someone responsible for the Fukushima Daiichi nuclear power station accident, I also feel a strong sense of duty. With this in mind, I am fully committed to seeing the decommissioning of this plant through to the end.
This trial retrieval of fuel debris marks a new stage in the decommissioning process. The Fukushima Daiichi nuclear power station will continue to leverage both domestic and international expertise to undertake this unprecedented, decades-long effort to retrieve fuel debris from its 3 reactor units.